All right, everybody, we're back. The question now is, what is carbocation rearrangement? Sometimes we generate a carbocation like this that starts off as what substitution? You look at the carbon with the plus charge and count the bonds it has to carbon. 1, 2. Started with a secondary carbocation. You're allowed to move an atom from an adjacent carbon and bring its electrons in the bond with it. And in this case, we're calling this a hydrogen shift. And it's going to make a better carbocation. The H is now here and the octet is full over there, but you moved it away from a carbon that used to have 4 bonds. So now the carbon has only 3. That is a new carbocation. By moving the H atom, you created a new carbocation that is more stable. So all 3 questions are basically answered here. What is a carbocation rearrangement? Well, it goes from this carbocation to this carbocation. What does it look like? Well, it looks like this hydrogen took its pair of electrons and moved next door. It did. And as a result, carbon here is now the cation. When does it happen? And the answer to that is quite simple. When a more substituted, let's be more general than that. More stable. One way to be more stable is to be more substituted. When a more stable C plus results. You can move a hydrogen from an adjacent position, or you can move a carbon from an adjacent position. So say we had this carbocation right here. And we did a carbon shift. Took one of these methyls and moved it to the next carbon over. Now, this carbon has 3 bonds. This methyl moved. The carbon down here had an H and 2 bonds to carbon. Now it's got an H and 3 bonds to carbon, full octet. Carbon above lost a 4th bond, so it's down to 3. And why did it happen? Because we went from a less stable secondary carbocation to a more stable tertiary carbocation. I would like to point out there's another one that could happen here from the same carbocation, and that would be moving this bond right here. It didn't have to be a methyl. It's also a carbon shift. And it happens because it generates a more stable carbocation. Oop. Nope, doesn't have that same skeleton at all. Now, what happens when the ring changes size? Well, if you're like me and you have trouble visualizing these things, draw everything except for that broken bond. Don't move a thing. And that goes up to here, and we have a methyl and a methyl. Now, this carbon here is this carbon. It's going to end up bonded to that carbon. So I'll show it in blue. This is the bond that moved to an adjacent atom right here. So it's got a full octet down there. Full octet. And the cation's here. Also tertiary. Also tertiary. So I don't see any reason why this would be better than this one. Both ring sizes are pretty nice sizes. Ring size 5 is pretty stable. 6 is pretty stable. They both generated a more stable tertiary cation. And at this point, let's illustrate some things that won't happen. I'm going to take my first carbocation right here and try a carbon shift on it. And I'm going to tell you why it won't happen. There's no reason to go from a secondary carbocation to another secondary carbocation. Not more stable. In fact, you could argue it's the same cation anyway, but it won't be happening. There's no reason for it to happen. So these won't happen. We got to make sure that's clear, that they will not happen. The reason is you didn't generate a more stable cation. Similarly, let's take this carbocation and try an H shift on it. Oh, where is it? It's here. C shift, top one. Oh, that's big. And the bottom one won't have an H shift happen. Same reasoning. Don't like that when that happens. And we could take this H here. We could try. Take its electrons. Move next door. And you'd be going from secondary again to another secondary. No motivation for that. So it won't happen. It's secondary. Not more stable. Thinks the whole thing's related. All right. So you can move a carbon from an adjacent position or a hydrogen from an adjacent position. And the only reason you would do it is to get a more stable carbocation. Let's go to my favorite rearrangement and then put this all together. Here's my absolute favorite. We got this cyclobutane, cation here. This one will happen. This one won't happen. Yeah, let's just show them separate too. You might think this is a great idea. Nope. Let me tell you why it's not. Sorry. Say, I'll move that H over there and get from a secondary to a tertiary. That's great. Why is he saying this one won't happen? You have an sp2 C plus ideal angle equals 120 forced into a cyclobutane, forced into cyclobutane, and you know the angles of cyclobutane are close to 90. Angle equals 90. This is terrible. Angle strain. Worse than the angle strain you learned when you learned about conformations. At least they were SP3 back then. Now we got a difference of 30 degrees, which is awful. So what's the consequence? This is not going to be happening. This one's great. Getting a little thick here. And once again, if you're having trouble visualizing these, do not move anything. Just don't draw the bond that you just broke. So there was a square. It's missing one side. It went up to here. And the bond you moved is here. And the cation, where's the cation? Cation's right here. I want it to be clear that there's an angle in there. All right, so let's do it here. That's a cation. He's saying, wait, he said you're not going to go from secondary to secondary. There's no reason to do that. Angle and torsional strength. Strain. That's a big fat check mark. That's a great thing. That has nothing to do with substitution. We can't forget the stuff we learned previously in this class. I think I misspelled relieved. It's one of those exceptions to the I before E except after C. No, I think it's right. It's not one of the exceptions. I'm sure somebody's going to get back to me on that. Yeah, it's good. Yeah, this secondary is a heck of a lot better than this secondary. This one's got cyclobutane in it, which is innately unstable because of angle strain and torsional strain. So yes, I like that top one. I do not like the bottom one at all. So let's come up with a test question. We'll do it right now. We'll do it together. See how the sausage gets made here. Save as. Intro, page 2. We're going to start, we'll do an HCl reaction. Get rid of titles. And what are we going to do? We're going to start with different stuff. That's what we're going to start with. Got our cyclobutane. And we got our double bond. And let's make it more interesting. I'll have stuff down here. So I want to give a mechanism for all products here. Give a mechanism for all products. Circle, major, and explain. Okay. So we can get this product here, where the chloride went there. We can get this product here. I'm going to go wide on this one. And that would put the Cl on the end. I don't think I'm going to get a lot of it. So give a mechanism offer for all products. Circle major. Okay, and we're going to have 2 rings. Oh, what did I do there? Hit my thumb on something. There we go. You have 2 products where the ring got bigger. You have this one where the ring got bigger. I'm going to move this bond to here. Move this bond to there. So you have a methyl up there. Goes to an OH here. Dimethyl here. And I hit my thumb again. Okay. And you might not be able to see that right. Yeah, I got 2 programs open. And we're going to get a Cl. And there's another one. I keep doing that. There's another one. Stop hitting that over there. Where I did the one where I moved that bond. I could have moved this bond up to here. In which case we'll go dimethyl, methyl. I can cheat on this one. Chlorine is going to be on the top. This will take us to the end of our segment. I got this coming up over here. And you want a nice blank version to work on your own. Okay. So we're integrating everything we've learned today. I have HCl, strong acid. All day, what have strong acids done to our alkenes? What have you done? You've taken the pi electrons, the most reactive electrons in this molecule, by the way. You always react pi before sigma if you can, and that's too chunky. Still a little chunky. I like the second one down here. That's the one. And you make 2 carbocations. Direct carbocations, you have 2 carbons involved in an alkene. Every time you react an alkene to make a cation, you're going to get a little more of this one than this one because it's more substituted. First one is secondary, second one is primary. I'm going to move this down a little so it doesn't look like it's, no. There. Has 2 bonds to carbon. It's more substituted than this one, which has only 1 more bond to carbon. So I've made more of this than this. And this one, when you made both of them, actually, you made a chloride. If you make a bond from chloride to this end carbon, which product did you just make? You are correct. You made the second product. Done with the second product. Now, this first one here, it's going to do that to me, isn't it? Thinks they're the same. Let's see what I got. That's fine. Got extra stuff, that's all. If you make this bond right here, this will make the first product, which you can't see anymore, but that's right up there. So you got half the products accounted for. Blue. And how do you know that both of these are going to come from rearrangement. Well, there's a couple clues. Big clue, the rings are different. Question 2 is, which cation can rearrange? And I haven't told you what the quickest way to figure out is of which cations can rearrange and which can't. And here it is. You ready? You go to the adjacent carbon to a cation and ask yourself, is this carbon branched? And you say, heck no, it doesn't even have another bond, let alone a branch. A branch would be 2 more bonds. That's not a rearrangement candidate, this cation. But from the left, it's branched. Look, carbon goes one way here, another way there. This is a candidate. This position is a candidate for rearrangement. A branched carbon, one away from a carbocation, makes that cation a candidate for rearrangement. And there's 2 ways to rearrange this to more stable cations. So I am going to copy again. You have to spend this time, because when you do a mechanism and you have some of the molecules doing one thing and some doing another thing, I've had students try to do 2 things on one molecule. That's insane. Molecule can only do one thing at a time. Don't reinvent reality. You can either rearrange here or rearrange here. Does it follow the rules? You take a bond away from the adjacent position to the cation and move it towards the carbocation. That's the only rearrangements you're ever allowed to do. I could have moved a hydrogen, but that would have kept the square intact. If I had taken it, I'm going to show it for 2 seconds. If I had done this, it's a waste of time because none of the remaining products have that square, and this would still have a square. And you were trying to show 2 things on one molecule at the same time, which I told you not to. So draw me the result of the 2 rearrangements. Result number 1 will be there. Result number 2 will be here. Draw everything except the bond that you broke. Just copy it as you see it. Doesn't have to be pretty. And the bond you broke went from this position right here and ended there. So it's from there to there, and the cation is there. Where you moved away from, this position never got a 4th bond. It lost its 4th bond. Similarly, copy everything except for the bond you're breaking here. Don't copy the bond you're breaking. And this one's a little easier to visualize, I think, as you see the bond happening from there to there with the cation on top. Let's put it where it belongs. Whoa, that wasn't very nice. There. Right on the carbon. And these 2 species will become, look at this, dimethyl, then carbon with a chlorine, then a methyl. Dimethyl, carbon that's going to have a chlorine, and then the methyl. Methyl's there. You're going to need to do another chloride. Just write it down somewhere. Yeah, the rearranged one needs a chloride too. You can't use a chloride for 2 different things. Please don't. Don't find out the hard way. That's going to cost you a whole point. Having one chloride go towards 2 different molecules doesn't happen. So draw me a new chloride for every product. And that would give that one. And this over here will give this one. And that finishes that segment. So that's how I combine one of our first mechanisms with these rearrangement steps. And these are rearrangements here, going from this ring size to this, or this ring size to that. And that will bring to a conclusion our discussion of carbocation mechanisms. And right after the break, we'll do an introduction to triangle mechanisms, which we'll spend a good hour on, maybe even a little longer, on Wednesday. So I'll see you after this break.